Hi, we're Team 1. Our team members are Taylor, Nash, Callie, Ashanae, and Alec. Our overall team task was to provide a rehabilitation system to assist handicapped individuals while they walk, drive, sit, stand, and walk on different terrains, and also including the stairs. Our design approach was to design an exoskeleton that can strap the individual in a power walking motion that's safe, economical, lightweight.
Next, I'll be talking about the requirements and how we met each of them. To make our device scalable, we made the upper leg and the lower leg both adjustable. This allows it to be used by any ages and with any heights. For movement and walking, we made it so that this machine can be used with any level of lower body paralysis. And how it works is the sensors measure the muscle strength and supplement this with the power from the motors. And if you cannot move your muscles at all, there will be a user-controlled function button that can control when you want to walk. Movement over various surfaces is accomplished with the ankle joint. The foot is spring-loaded as a spring-loaded hinge that will allow for some slight tilt, and also we can walk up slopes with the same process. We chose an exoskeleton because it is able to traverse stairs. We also added the crutches for stability and balance. An electric wheelchair and walker cannot go upstairs, and that's the main reason why we picked the exoskeleton. Next, I'll be talking about power. And to start, we created a duty cycle of when we thought the person would use this device during the day. And this consisted of 3 main functions. First was walking around the office. Second was the exercising in the evening, and also the 10 flights of stairs that they'll have to traverse in a day. So to calculate the power, we used Dr. Hassel's slides, and I calculated the average watt for every step. And we multiplied this by the amount of time that we calculated in our duty cycle that they would be walking. And we came up with a needed capacity of 25.3 amp hours. To supply this, we're going to use 3 absorbed glass mat lead acid batteries, and they're very safe and shock resistant, and that's why we chose them. And they'll provide an extra 10 amp hours that will be used to compute the sensors and the computer power.
Hi, this is our SolidWorks model, and I will be giving a brief tour. Located here is our lumbar back support, which will be made out of ABS plastic and will also have padding. On both sides, we have 2 bars that connect our lumbar back support to the hinges at the hip. These hinges allow for 3 degrees of freedom. Our upper and lower legs have adjustable pins. These adjustable pins will allow for different leg lengths. We have 2 spur gears, one located at the hip, one located at the knee, and one located at the ankle. Attached will be our motor that will then drive the smaller spur gear, which will then rotate our bigger spur gear. We have 1 pin located at each side of the ankle, made out of A307 steel, and will allow for a rotating motion at the ankle. We have 2 feet supports that have straps to safely secure the individual. And I will also show a rotating motion of our gears.
For the bearings, we're going to use 1 bearing at each hip. And the kind of bearings we use are narrow bearings that gives us advantage of small space. To calculate the max load, we assume the user will lean on one side, gives us the static load, and from there we get the C0, that is the smallest bearing. To calculate the gear forces, we use the motor features, the horsepower, and the rotational speed. From there, we were able to calculate the tangential force and the radial force that acting on the main gear.
These are our critical elements. To determine that, we used a 95 percentile, 250-pound person, and the suit is 75 pounds. That totals to be 325. However, 25 pounds is taken from the crutches, so our max load is 300 pounds. Picture of our design with the critical elements. We decided that the pins down low are going to be the most critical ones because they're the most weight bearing, And that's going to be the pin at the knee, the adjustability pins in the lower leg, and the ankle pin. So the adjustability pins, while we do have them up in the upper section of the leg, as I said before, we determined that this section will bear the most load because it's where the most weight is acting. And so what we decided is if these pins can support the load, then the ones higher up will have no problem. So for our pin static load, the actual pin that goes in, we used a A307 steel, and I calculated the cross-sectional area of it, and then went through the stress analysis and took our force, which was 300 pounds, and then divided by the cross-sectional area to get our stress, and we calculated our factor of safety, which was rather large, 17.4, which to us makes sense because this is a pretty strong bolt, and we're only putting about 3,400 psi on it, so it's expected the factor of safety will be large. For the area underneath the pin, the carbon fiber that is being stressed, we used essentially like a half pipe, and I calculated the area that, and did the same stress analysis, sigma equals V over A. Used the same weight force, the area was different, and since carbon fibers ultimate strength is 70,000 and we only had a stress of roughly 1,000 psi, our factor of safety came out to be a lot larger, which once again is expected.
Okay, so as far as static loading goes, we chose to focus on the ankle pin first because it's going to have the most weight. It's going to have everything above it. So looking at that, there's our design of our ankle pin. The pin is in between the lower leg and the foot. Due to the adjustability of our leg, the leg itself is hollow, where it attaches to the ankle at the foot, and so the foot comes up in here, and then the pin goes through it. So that's our design right there, which leads to our free body diagrams and then our shear and moment, and that's how we got the values for these calculations. We started out with simple shear, as Alec has already talked about. That's how we calculated that, and that gave us a safety factor of 30. And then bending, we calculated that with I, because it's in bending, that's why we used I, and we got a safety factor of 1.24. So the ankle pin will not fail in static loading. And then we looked at the knee pin for fatigue loading. Looking at Dr. Hassel's slides, the knee has the maximum torque while climbing stairs, and we use the climbing stairs because that's going to be a higher torque than walking, because it's going to be a higher power and everything. And then to calculate the knee pin fatigue, here's our initial values. And going forward, we calculated the endurance strength with all of those K values. We got to an endurance strength of 21 kpsi. And then we used von Mises stresses to integrate the static loading, and both will be alternating because we'll be going upstairs. So there'll be pressure on that foot as it climbs, and then less as the other one climbs, so it'll be alternating stresses and torsion. And so putting in the von Mises, again, there's no stress concentrations because these are pins that we're calculating on the ankle and the knee both. And then plugging that into the modified Goodman, we got a safety factor of 0.136.
For every design, it has issues and mitigations. Our design, we included the extension cord in case the battery capacity does not exceed. Also, our design is not suitable for certain weather conditions, such as rainy weather. For this moment, currently, our design is based on analytical, mechanical calculation, and hypothesis. Thus, we would like to recommend a lab testing before manufacturing. In conclusion, we have achieved the requirement, which are the 12 battery capacity for the design, and it's suitable for most users because of the adjustable frame. And for those subcomponents, our least factor of safety is the knee pin that has 0.136 factor of safety. Thus, we would like to recommend to change the metal, the type of metal at the knee, or change the diameter at the pin. And this concludes our presentation. Thank you for watching.